Okay, let's try and slightly accelerate and see how much of these topics we can cover. Um, so let's start again with span of vectors. So now you know how I speak. You can probably follow a little more. Is the audio coming through? Can you hear me okay there? Okay, cool. So let's hopefully we can slightly accelerate and see how fast we can cover or what topics we can cover. In the worst case, we might not talk about eigen vectors, or we'll talk about it very briefly. Okay, so let's start again just for continuity's sake. The span of a set of vectors is their linear combination. Let's say v1, v2, vn in a vector space V is their linear combination. Okay. Then definition, linear independence. A set of vectors is linearly independent if and only if the scalars for their linear combination to produce the zero vector is all zero. Okay, cool. So with these two, we can define the following bases of a vector space. A set of vectors in a vector space is called as a basis if they span the vector space and are all linearly independent. Okay, so and then we'll define dimension of a vector space. If the basis for the vector space is finite in number, their cardinality is called, the number of such basis elements is called the dimension of the vector space. And finally, a vector space is said to be finite dimensional if its dimension is finite. Okay. Yeah. Question? No. Cool. Quick examples. Let's do to cover all these ideas. So let's say we have E3 is our vector space, then 1 0 0 0 1 0 0 0 1 can be checked is a spanning set of vectors that are linearly independent. Okay. So this is a basis. This is the standard basis. Okay. As non-examples in this context, 1 0 0 0 1 0 is linearly independent but not spanning. With something else added, with another vector added, let's say, is spanning but not linearly independent. Thus, neither is a basis. Okay, and as a result, the dimension of E3 is 3. It's a 3-dimensional space. And the same thing could have been, I could have done this by replacing this with En and writing down n-dimensional standard basis vectors, and I would have gotten the dimension of En is n. So I could have, I can totally extend this argument to En as well. Okay. Okay, so let's consider, let Pm of x denote polynomials up to degree m. Okay, so this is not the P of x, this is polynomials up to degree m. Yeah, so Pm of x is going to be things like a0 plus a1x okay, as an example. And if you feel like you should try this out as an exercise, or maybe the TA in the afternoon will talk about it. Azhar, I don't know if he's here, but okay, so for Pm of x, which is also a vector space, those are m plus 1 elements. There are m plus 1 vectors. The set of m plus 1 vectors is both a spanning set and a basis, and linearly independent. So of course these need to be verified. So but I'm not going to try and verify, show that formal proof in any detail. You can try this out as an exercise. Is both a spanning set and linearly independent, and hence this is a basis. but this is like any vector space will have many bases. Okay, and so I'll give you another example of a basis. So just take x minus 1, the same argument, this is another basis. And as a thing to look online, this set of so-called Legendre polynomials will also be a basis. There are many examples of basis. Then there's Lagrange polynomials will be a basis, Newton polynomials will be a basis, but Legendre are a so-called orthogonal basis, but it's not relevant to our discussion. So if you want, you can totally, this is tangential and you can look online. Okay. So at this point, usually I would ask in a course setting, will the space of polynomials of degree m be a vector space? So here I've written up to m, but will space of polynomials of degree m be a vector space or a vector subspace of the space of polynomials? So that's a question for you. Again, exercise is the space of polynomials of degree exactly equal to m a vector space. Okay. Anyone knows the answer by any chance? It's not is the right answer, but why? Yeah, yeah, yeah. No, that's not what those are the lean sets of R2. So that's not what we are thinking about. I agree, but then that was the map, the so-called graph of it, or the like the curve that we draw was parameterized or could be described by x square, and we think of it as a subset of E2. Okay, so that is not quite the reasoning. So this is not because of the polynomials as a vector space are not subspaces of En or anything like that. In fact, they are subspaces of some infinite dimensional space, but or the set of polynomials at least. But that's not the argument here. So do you have an alternative? It does not have. No, it has. What could happen is if you add two things, you could not land back. It's not closed under. It does have the zero. The zero. I mean, okay, it's exactly m. I said okay, it doesn't have zero is a good enough explanation. But another explanation you can think of is I can add, just delete the m by adding two polynomials. I can get rid of the mth order term, and it will not be therefore back in the vector space. So that's fine. Zero is also a good answer. Okay. Anyways, so polynomials of degree up to m is a vector space and has a basis that is size m plus 1. So it's actually a finite dimensional vector space. So we can say dimension of, this is how you write dimension of the polynomial space up to degree m is m plus 1. Okay. What? Okay, so earlier I talked about a third example. Consider the vector space of this, sometimes you can say infinite sequences where x1, x2 are all real numbers. a basis for this space is of the form one, 0, and so on. Okay, you can verify that this is spanning and linearly independent. Okay. And therefore the basis here has infinitely many terms, because these are infinite sequences, or this is an infinite tuple. So the basis is not finite dimension. The basis has an infinite cardinality. So this space, which I had earlier, I think, said this is E infinity. So this is not a finite dimensional vector space. Okay. Cool. We did talk about one other space. Let's consider the vector space of continuous functions from 0, 1 into R. Okay, so this usually the notation for this is to say C on 0, 1. Okay, that's the notation. This stands for continuous. Sometimes people might put a C0 also, but if it's not there, that's okay also. It's or C of 0, 1, and this just tells you where the domain is. Okay, since any continuous function may be approximated, so there's a lot of so-called measure theory I'm hiding, but you could imagine as a first cut, you could write down Taylor series for, I mean, there might be troubles at singularities, and we are not thinking about some pathological functions, but you could imagine that these are well approximated by Taylor series at most points. Okay, the formal way that people will say, if you take a course in second course in real analysis, for instance, is to say that polynomials are dense in the space of continuous functions, but I'm not going to write it down. You could imagine, it makes sense, right? If I had some function, I can write down its Taylor series. It's a continuous function, fine. Maybe the Taylor series doesn't exist at a bunch of points, but maybe I can write it around some convenient points. It's still valid in some small enough regions. So this is just intuition, by the way. I'm not giving you the formal proof or formal argument here. So since you can imagine, you can write down Taylor series, the basis, thus a basis for C 0, 1 will be at least similar to a basis. What is similar? I mean, I'll put it in double air quoted, similar to a basis for the space of polynomials itself. If you want, we can say space of polynomials on 0, 1. So the previous x, I could have said P of R, but I used P of x, but imagine these are space of polynomials on 0, 1. So this will be therefore, so a basis for, let's say, basis for P of x will be, by analogy to what we wrote down, a basis like this, which is infinite dimensional, and similarly the dimension of the space of continuous functions is infinite. Okay, so it's a bit of a loose argument, but intuitively it could make some sense. Yeah, because any function I can write as a Taylor series, and therefore is like a infinite degree polynomial, and so the bases will be infinite in number. So that's another example of an infinite dimensional vector space. And one last example I'll leave with, which is a slightly new space. The space, the trouble with this is I'm going to have to come back to it maybe. The space of M cross N matrices with real entries. So this space is denoted Rm cross N, is a vector space and a finite dimensional one. So I presume everyone knows what a matrix is. So and the dimension, so this is also sometimes notation. Okay, maybe that's not important, but so I'll just say that notation for that notation is usually M cross N, or M of M comma N is the space of M cross N matrices, and its dimension, you need to verify that this is a vector space and so on, will be M into N, the product of this. You can think of this as one long vector, and you can think of a vector, an n tuple space is of dimension n. So I can think of writing a matrix as this very long vector. I could just assemble all the columns into one long vector, and so you could imagine that this sort of makes sense. Yeah. Okay, so for today's discussion, rest of today's discussion, we'll only focus on finite dimensional vector spaces for rest. Okay. So we have vector spaces, we have some idea of what bases are, we know that defines the dimension. So I have now I'm kind of equipped with finite dimensional vector spaces. We shall next, remember this is also some optimization refresher. So the next thing you could do in building one's toolkit is that, okay, I have in one dimension, once I knew how to do real number arithmetic, I could then define functions between R to R, for instance, and then do calculus with that function. So we won't do calculus here, but at least let's think about defining functions between finite dimensional vector spaces. Okay, so functions between finite dimensional vector spaces. So we'll say let t, we'll call it t, be a function from u to v, okay, where t is a function that takes an element u in U and produces a vector v in V. Okay, so my u's and v's might look similar. Let me write it down like that. Yeah. So t of little u is this little v. Okay. So remember I said that a key feature of vector spaces is linearity. Okay, and I don't want to kind of destroy this feature when I'm thinking about functions between finite dimensional vector spaces. Okay, so let's assume, or let's presume, that we want the function that we consider to preserve the linearity character of vector spaces. Let's for a moment presume that we want this is special and we want this to be preserved. What does that mean, right? So this means that if u1 and u2 are in this space U and my function t acts on a linear combination of these vectors, we demand the following then. Okay, so what do we demand? Let's say t acting on u1 spits out v1, t acting on u2 spits out v2, and t acting on c1 u1 plus c2 u2. I demand, so this equality is by requirement equals c1 t of u1 plus c2 t of u2. Okay, that is, this is equal to c1 v1 plus c2 v2. Okay. There are many functions you can consider between the spaces u to v, but we are interested in studying or considering such functions for the moment which preserve this linearity structure that we have for the vector spaces. This by definition is what is called as a linear function. A function that has this property is called linear function. So a function t from u to v which has this property by this property I mean this property is called a linear function. Okay, so when we are considering functions between finite dimensional vector spaces, we are going to consider what are called as linear functions. Okay, we don't have to, we can study functions that are not linear, but as a first cut or as a first thing to study, just like we can study parabolas in R2 or cubics in R2 as sets of R2, but or E2 let's say, but we are not doing that because that doesn't have that linearity structure as a subset, so it's not a subspace. Similarly, we can study like there's infinitely many functions between finite dimensional vector spaces, but let's focus on functions which preserve this character of vector spaces, which is linearity. So linearity is like at the heart of linear algebra. Of course, that's why it's called linear algebra, but what it means is that it's at the heart of what vector spaces and subspaces, how they are related, and we are going to study functions which are also linear between these finite dimensional vector spaces. Okay, so we will therefore focus on functions which are linear functions between finite dimensional vector spaces. Okay, so now we have imposed another structure, another requirement on the functions that we are studying. So T is a function between u and v, and we demand that it be linear. So examples, what are such examples, right? So let's look at some examples. So let u equal polynomials of degree up to m plus 1 and v equal polynomials of degree m. Okay, then we let t of x equal the derivative of p of x for p in pm plus 1 of x. Okay, so claim t of x is not t of x, I should just say t of p. Claim t is a linear function. Why? Because why is t a linear function? Right. So I mean, all of us have some background exposure to calculus as well, and derivation is a linear property. I mean, is a linear function. Like derivative of f plus g is derivative of f plus derivative of g. Okay, so this is a linear function, and it is between finite dimensional vector spaces. So this is an example of a linear function between finite dimensional vector spaces. But we are not doing derivative of any arbitrary function. We are doing derivative of polynomials of degree m plus 1, which will give me one lower order degree polynomial. We know that polynomials of degree m plus 1 is finite dimensional space based on the example that we saw, and similarly degree polynomial of degree up to m pm is finite dimensional. So this is an example of a linear function between these spaces. Okay, by the same understanding, we can do let u equals pm of x, v equals pm plus 1 of x, and the function t of p is the integral over whatever appropriate domain, is the indefinite integral, let's even say, with a constant set to 0 for whatever purpose, or it can have any constant, it doesn't matter. So let's forgetting the details. T of p is the integral of p of x dx for p in degree m polynomial is another example. Is another linear function between finite dimensional vector spaces, because integration is also linear in the arguments. Yeah, cool. We can do other linear functions too. Let's presume u is R3. Okay, we didn't talk about R3. Let's say u is E3 and v is also E3. Okay, so now I have to take a vector and spit out another three-dimensional vector, or a 3-tuple and spit out a 3-tuple. Okay, here is an example. t of x, y, z equals x plus y, 2x plus 3y plus z, x minus z. Okay, so for every point in E3, I'll give you again a point in E3 using this function, and again you can verify that this is a linear function because it's chosen to have nice linear combinations. And so this is another example of a linear function between these two finite dimensional vector spaces. Okay, so let's do some theory building, little more theory. So let me first write down the claim. Every linear function between finite dimensional vector spaces has a matrix representation or realization. Okay. So what does this mean, right? And this is how it's going to be related to matrices. So definition, M cross N matrix is a collection of M n numbers in M rows and N columns. So if A is an M cross N matrix with real entries, so that's why let's say with real entries, it could have other entries too, but since our theme is real, we'll stick with real valued matrices. So A is going to be then of this form, something like A is 0 0, A 0 1. So I should maybe use A1 1, A1 2, A1 n, okay, where each Aij is a real number. Okay, so this claim is saying that every linear function between finite dimensional vector spaces can equivalently, that's a function like maybe even this, can be thought of as having a matrix representation. Okay, so here is the, so is that statement okay with everyone? It's not something, again, if you have seen it in a linear algebra setup, great. So so essentially what this means is any t u to v can be thought of as acting on a u in u via a matrix vector product. So you have matrices, and matrices can multiply with themselves and can multiply vectors to produce other vectors and so on. So this is what we can think of, that so here is a fancy way of representing this. So I have between u and v a linear map that's same as some matrix multiplying since I haven't introduced R, I'll say En to Em, where dimension of U is N, dimension of V is M. Okay, so there is something here, and this is just a fancy way of saying things. You don't have to worry about if you don't know what this is. People will say that this is a commuting diagram. But I've parenthesized it because it's not so important. But essentially what this says is, if I have T acting on U to produce V, I can think of that as A acting on some element n tuple vector to produce another number which can be related with these vector spaces. Yeah. So for example, again, examples might illustrate what I'm trying to say. Example, if U is this, I can think of any element U in P of M of X is a degree up to degree M polynomial of the form something like A0 plus A1x plus AM x to the power M. Yeah. We already saw that this is a finite dimensional vector space. Dimension of Pm of x is M plus 1. You could say equivalently, U can be described by the M plus 1 coefficients. Okay. So if I have, so this is the duality. I have Pm of x, I have A0 plus A1 x plus Am x to the power M, and here I have Em plus 1 where elements are of the form some A0 A1 Am in this case. Okay, so this in this vector space, vectors are polynomials of this form. In this vector space, vectors are M plus 1 tuples of this form, and we can say there is a 1-to-1 correspondence. Which means if I gave you a polynomial, I could just extract it, a degree M polynomial, I could extract its coefficients and give you a M plus 1 tuple. Okay, does that make sense to, I mean, to most folks at least? Because if you are from engineering, I don't know if you necessarily see this kind of stuff in linear algebra. So is this making sense? So all I'm saying is, it doesn't matter how I describe polynomials. I mean, polynomials are described by their coefficients, right? It's a degree. Once I tell you the degree of a polynomial, x square has coefficient 0, 0, 1, right? 0 for the constant, 1 for the linear term, 0 for the constant, 0 for the linear term, and 1 for the quadratic term, this x square term. X square plus 2x plus 3, the coefficients are 1, 2, 3, right? So given a polynomial, I can extract the coefficients and write a tuple, which then can be thought of as an element of the vector space Em or Em plus 1 in this case, right? So, and I can go the other way around too. If I gave you an element of this space, I can construct a polynomial out of that. So if it's whatever is the length of that tuple, I'll assemble a polynomial of degree 1 less than that, right? So for example, just to make it concrete, x square plus 3x plus 5 is the same thing as 1, 3, 5, or maybe something like x to the power 5 plus 1 is the same thing as 1, 0, 0, 0, 0, 1. It's an element of E6. Okay, So I can go both directions. Given a polynomial, I can write down an element of this Euclidean space, or given an element of the Euclidean space, I can write down this polynomial, right? So we say such, I mean, without getting too bogged down with the details, when we can do this, we say that the spaces are isomorphic. When we can write down such a one-to-one correspondence, we say that the spaces are isomorphic. Okay. So thus the space of polynomials of degree m is isomorphic to em plus 1. Okay, so